Okay, so let me follow up on something that we saw at the end of the last class, right? When we were using those Mathematica examples to calculate stuff, right? And in particular, when we were working with those examples, we found what's the average x and the average x squared. And from those, we got the standard deviation, which we could interpret as the uncertainty in x. And then we did the same thing with momentum, right? That we got the average momentum and the average momentum squared, and then the standard deviation sigma p. All right, and so that's something which we could interpret as the uncertainty in the momentum. Okay. And then just at the end of the class, I pointed out to you, what do you get if you multiply these numbers, the uncertainty in x times the uncertainty in momentum, right? And in the first of the two demos, this product came out to be exactly equal to h bar over 2. Okay. In the second demo, well, it came out to be a mess. Right? It involved time. It involved this constant alpha that I introduced. But if you plug in numbers for alpha and time into that mess, you always get something that's at least as big as h bar over 2. It's generally bigger than h bar over 2, but it's never smaller than h bar over 2. So I'll say it's greater than or equal to h bar over 2. So, these two cases are examples of what we say in general as the uncertainty principle in quantum mechanics. That is that the uncertainty in x times the uncertainty in momentum is greater than or equal to this quantity h bar over 2. Later on in the course, much later in the semester, I'll give a general proof of that and apply it to other kinds of variables besides position and momentum. But for now, let me just say a couple of ways to interpret this uncertainty principle, regardless of the mathematical proof. Okay, and so we could say for like general considerations about the uncertainty principle. And one thing that we could say is that it just arises from the wave description. We haven't really done anything yet with solving Schrodinger's equation. All we've done is talk about, what are the consequences of having matter that's described by waves? And so here we're seeing that whenever we have matter that's described by waves, we have to have a position that you can average by putting the x in the middle of this integral sandwich, right? And that is to say, we get this average of x is an integral of psi star x times psi. And we have to have a momentum that corresponds to putting this derivative operator, the minus I h bar d by dx in the middle of the integral sandwich. Right? And then, if we define position and momentum in this way, we automatically get the uncertainty principle. It's a consequence of working with waves. We can't avoid it. Right? And one way to interpret it is to say that the momentum corresponds to a wavelength of the wave. And these things are related by what's called the de Broglie formula. i.e. de Broglie formula, which says that the momentum is 2 pi h bar divided by the wavelength. Okay, this lambda is the wavelength. Okay. And you can see that makes sense because when you have a wave with a small wavelength, it goes up and down a lot. So, any wave with a small wavelength looks something like that, and it goes up and down a lot, right? And when you have a long wavelength, maybe it looks something like this, right? It doesn't go up and down so much, right? And so we know from this kind of relation up there that the momentum is associated with derivatives of the wave. And so when you have something with a small wavelength, and it goes up and down a lot, it has big derivatives. Right? Whereas if it has a long wavelength and it doesn't go up and down so much, then it has small derivatives. Okay, and so the low wavelength has a high momentum, and the long wavelength has a low momentum. Right? And then the uncertainty in momentum corresponds to uncertainty in the wavelength. So we have to say, for a wave, how well do you know the wavelength, right? Now, if you have a situation where there are a lot of waves, where you see the same wave repeated many times, something like this, then you know the wavelength pretty well, right? You know it pretty well because you can say, oh, well, there's the spacing between there and there, right? So you can look at the spacing between many wave fronts. Maybe it's 6 wave fronts that I just drew, but maybe it'll be 600 or some big number of wave fronts, right? And so if you see a lot of wave fronts like that, then you know the wavelength very well. we'll say you know the wavelength well, which means that the uncertainty in wavelength is small, which means the uncertainty in momentum is small. But when you have many wavefronts, that means that the wave is pretty spread out over a big region. And so you don't know the position very well. So that means that the uncertainty in X is large. So that's one limiting case, right? Where there are many wavefronts and you know the momentum and the wavelength well, you don't know the position well, right? The opposite limit would be something like this that just has, a single spike or a few spikes in it. And here you, I'll say, few wavefronts. You know the position well. That is, sigma x is small, but you don't know the wavelength well. So the uncertainty in the wavelength is large, which means that the uncertainty in the momentum is large. So here we have a trade-off, right, between the uncertainty in position and the uncertainty in the momentum, right? That you can optimize one of them, but it makes the other one worse, right? And so this trade-off is what gets expressed by the uncertainty principle, that the product is greater than or equal to h bar over 2. Now, you'll notice this is an inequality. Okay? That means the best case is that these things are equal to h bar over 2. And then when one goes up, the other goes down. Okay. Now, you can do worse than that, right? That's the best case is h bar over 2, right? You can always have situations where you don't know either one very well, right? That's some case where there's extra uncertainty, right? But the best case is h bar over 2. So my demo number 1 in the last class, right, that's one where it matched the best case, right? The product is exactly h bar over 2. My demo number 2 is a little bit worse than that. And so that's what you could see if you tried putting in numbers for this alpha parameter and see numerically what's the product of the uncertainties in position and momentum. Okay, so that is the sort of general hand waving story, right? You know this expression hand waving, right? That's what physicists say when we're not actually calculating something with equations, but we just say, oh, one thing goes up and another thing goes down, and we move our hands around a lot like that. Okay, so this is the hand waving version of this story. Later on, I'll do a proof, but that'll be much later in the semester. Okay, so that's a story about the uncertainty principle. And so it's something that we could check in the examples that I did in the last class, and it's something that you can check with future examples, which reminds me, that brings me to the next thing I wanted to say, which is that I've now posted a homework for you. All right, so there is a homework number 1, which is posted on the Google Drive. And I made it due on a week from today. So that is whatever it is, Thursday, February 4th. Okay, so please download it and work on it and do it and email it to me on February 4th. Okay, two quick comments about the homework. One is that there are 3 problems. No, there are 4 problems. 3 of the problems are things from the Griffiths textbook, and I just copied them out of the Griffiths textbook to make sure that you know the numbering, and you do the same one that I've assigned. Okay, the 4th one is a Mathematica problem that I made up, where I ask you to take the demo number 1 file that I created and put in a different guess wave function or sample wave function on the top, and then see how everything works out after that. And so one of the things that you'll be able to do is to check the uncertainty principle for this alternative guess that I made there. So instead of an e to the minus x squared, there's some different dependence on x. And you can check how well the uncertainty principle works out in that case. You know, that's not a lot of mathematical work. That's basically taking the file that I made for you and changing one thing in the first line and see how everything else works out after that. So please try that, okay? Now, I don't mean to make a lot of programming stress on you, okay? And so if you have a computer problem, like you can't get the licensing of Mathematica to work, or Mathematica won't run on your laptop because your laptop is too old or cheap or something like that, or you can't figure out how to type a Greek letter in Mathematica, or, you know, if you have non-physics problems, if you have computer problems that are not physics problems, don't get stressed out about those things. I don't care that much about those things, okay? The main point is to illustrate the physics, but if you cannot do that particular problem because of some computer issues, fine, whatever, okay, I'll deal with that. Okay, that's rule number 1 as far as the software, as far as the homework goes. Rule number 2, I think I forgot to mention this when I was going over the syllabus. When it comes to homework, I encourage you guys to work together. It is more than allowed. It is actually recommended. Okay, and so by all means, feel free to talk with other students in the class. Just, you know, don't infect each other with viruses, but you can talk online or email or whatever, right? But if you can find a safe way to communicate with each other, please do that. I think it is every professor's dream that students are actually talking about the class outside of class. I don't know how often it happens in real life, but that is something I would like very much. The only thing I would say is that when it comes to actually writing out your solutions for the problems, Don't just copy what somebody else wrote word for word, right? But, actually write it out in your own words. And so, you can feel free to talk with other students about how to solve the problems, but in the end, you should just write out the solutions in your own words, and that's what you can send to me. In this respect, the homework assignments are different from the tests. So the tests are places where you are not allowed to communicate with other students while you're doing them. Okay, and if you have any questions about what's allowed or not allowed, just ask me. That's fine. Okay, we good with all that? Great. All right. So, this kind of concludes what I wanted to say about chapter 1. Right? And so, chapter 1 in the textbook is just explaining what is the description of matter as waves. That is, such an important part of quantum mechanics. And so we're talking about things like, how do you extract information out of a wave function if you have it, right? But of course, that then leads to the question of, how do you get it, right? And so what we want to do now is to think about, how to solve Schrodinger's equation. And that's going to be the subject of chapter 2, and that's really a big subject. This is a big chapter. Okay, so let's move on to that now. So I'm going to begin talking about chapter 2, which is solving the Schrodinger equation. And in particular, solving the Schrodinger equation in one dimension. So if we just have the position in one direction, x, later on, we'll extend that to talking about solving Schrödinger's equation in 3 dimensions, x, y, and z. Okay, so here's the equation. Okay, so we have I h bar times this partial derivative of psi with respect to time, and that is equal to minus h bar squared over 2m. And the second partial derivative with respect to x plus the potential energy times the wave function itself. Okay, so how do we solve this, right? So that the name of the game is going to be that we specify the potential energy. So we say, are we working with, for example, a harmonic oscillator potential, right? We could say, for example, what happens if v of x is 1/2 k x squared? Okay, so that's an example of a potential energy function that you're familiar with in classical mechanics. And then we can say, well, what if we put that potential energy function into Schrödinger's equation? What do we get out if we want to solve for the wave function, right? The psi of x and t. Okay. So we have to specify the potential energy. Yeah, okay, solve for psi of x and t. Right. Now, this is a type of equation which is called a partial differential equation. Commonly abbreviated as PDE. Okay. And this type of equation occurs a lot in physics. And so Schrodinger's equation is one good example, but similar things show up in other areas of physics. And the main place where most students see it first in undergraduate physics is in electromagnetism. In electromagnetism, you talk about Maxwell's equations for the um, electric and magnetic fields as functions of position and time. Okay. And so for those of you who have already studied electromagnetism, here's a place where you will use the methods that you already learned. Right? And so, this what I'm about to do will be easier for you if you've already done similar kinds of solutions to get out the electric and magnetic fields or the electric potential function. On the other hand, if you have not yet studied electromagnetism and this is your first time doing things, that's okay. In that situation, probably you'll be getting to electromagnetism later. And the stuff that I'm doing now will be good preparation for that, right? And so this is the kind of mathematical method that all physics students need to do a few times in different kinds of situations. And when you do it in some situations, then it becomes easier to do it in other situations. Okay, so the method that we want to do to start with is what's called separation of variables. Okay, so what that means is we will make an assumption for the form of the solution. And our assumption is that the wave function, as a function of x and t, factorizes into a function of x times a function of time. So we could write it as a psi of x times some function of time, like that. Okay. So just to make sure that you can all read my handwriting for Greek letters, okay, this symbol is how I write the uppercase capital psi. This symbol is how I write the lowercase Greek letter psi. And this symbol is how I write the lowercase Greek letter phi. Okay, that's my Greek handwriting. Real Greek people might write the letters a little bit differently. I really don't know. Okay, so what we're saying here mathematically, is a pretty strong assumption, right? This is an assumption about, a function of x and time, which might involve x and time in some complicated combination of ways. And here we're supposing, well, maybe it involves x and time in a particular way, that it's a function of x times a function of time. Okay. This assumption is not always true. Okay, so I will say not all solutions have this form. Indeed, most solutions don't have this form, right? This is a very special form. Okay, so the reason why we think about solutions with this very special form is that the general solutions can be written as a sum of special solutions. Okay, so I'm going to search for this kind of special solution, and I'll find, not just one, but lots of special solutions, a whole family of many, many special solutions. And then I'll say, well, now we can add them up in the right way, which I will show you, to get a general solution of Schrodinger's equation. Okay, so that is the separation of variables method. Okay, and this is a powerful way to get pencil and paper type solutions for partial differential equations. Now, sometimes students ask me, why do I teach old-fashioned methods to get paper and pencil solutions? Why should they learn such old-fashioned stuff when there are all kinds of modern computer ways to get solutions to differential equations, right? For any old differential equation, you can type it into a computer and click go, and it runs for a while, and then it gives an answer, right? That's actually a really good question. I guess the answer is that it's good to be able to do a combination of things, right? And that each approach has its usefulness in different situations. The good thing about seeing the properties of special solutions and adding them up to make general solutions is that you really get a physical interpretation of what's going on. And it's a physical interpretation that can apply to a wide range of problems, right? Whereas if you tell the computer to solve something, you're telling it to solve the problem in just one specific situation, and you don't really know how general it is. And then if somebody comes and says, well, what if you adjust this one thing? What happens? And you say, I don't know. I guess I better punch it into the computer and see. And so it's good to be able to think of both. Okay, so I'm going to show you this kind of old-fashioned method, and you can learn that. And then I'll have some demos, not today, but in future classes, about what would happen if we just told Mathematica to solve the differential equation and see what we get. And then we can see how it compares with the paper and pencil type solution. Okay, so that's the strategy here. All right, so let's do it. Okay, and I guess one more thing I should say is at the moment, I will leave this v of x function just to be any general v of x. So for today, I'll see what do you get with just any old v of x. And then beginning next week, we'll talk about several specific examples of v of x functions and what you get from them. Okay, so let's do it. Okay, so I'm going to take this form of the solution and plug it into Schrodinger's equation. So here is Schrodinger's equation. Let me lasso that and I'll copy it onto another slide. Copy. Paste. Okay, this is what we want to solve. Oops, I can use this. All right, and now we're going to put in this separation of variables assumption. That is, that we're going to put in that psi of x and t is equal to lowercase psi of x times phi of t. Okay, and we put it in there. And we also have to put it in there. And we also have to put it in there, right? Everywhere where we see the psi. Okay, so now what does that do to Schrodinger's equation? Okay, well, let's go term by term. Okay, so in the left side of the equation, we have a partial derivative with respect to time. Well, if we take the partial derivative with respect to time of a product like this, well, the psi of x is constant with respect to time, right? It's a constant that factors out of the partial derivative. Right? So we just get IH bar times this lowercase psi of x times the derivative of phi with respect to time. Okay, that is equal to, let's go on to the next term. Okay, so minus h bar squared over 2m. Right here we have a second derivative with respect to x. So when we plug in this product, well, the phi of t is constant with respect to x. Okay, so it factors out. And we have the second derivative of psi with respect to x. Okay. Then we have to add on the third term, which is v of x times psi of x times phi of time. Okay, we're all good with that? All right. So now what? Okay, so now the next step in the separation of variables method is to divide through by the product of psi times phi. So we'll divide through by psi of x, phi of t in all of the terms. So here. And here. And here. Okay, so the nice thing about doing that is that we get some cancellation, right? So here the psi's cancel. Here the phi's cancel. And here they both cancel. Okay, now what's left after that cancellation? Okay, so on the left side, we have IH bar 1 over phi of t times the derivative d phi dt. That has to be equal to minus h bar squared over 2m, 1 over psi of x times the second derivative plus v of x. Okay. Now, there's a little trick. If we look at what's on the left side of this equation, this thing is related to time, right? Phi is just a function of time. So this involves time, this involves time. There's nothing here that has anything to do with x. Okay? This quantity, wrong pen, this quantity is independent of x. It might depend on time, but not on x. Okay. Now, how about the stuff on this side of the equation? Okay. Here, well, psi is a function of x. This second derivative is a function of x. This v of x is a function of x, right? There is nothing on this right side of the equation that has anything to do with time. It might depend on x, but not on t. Okay. But now you notice the left side is equal to the right side. Okay. So here is something that's independent of x, and here something that's independent of time. So you ask, how can something that's independent of x possibly be equal to something that's independent of time, right? There's only one way, and that is they both have to be equal to something that's independent of both x and time, right? They both have to be equal to some constant, okay? So we will set both of them equal to a constant, which I will call capital E, for reasons which I won't tell you now, but I'll tell you later. Okay, so this has to be a constant, which is independent of x and time. Okay, so that means that now we know the thing here on the left side, that has to be equal to E, and this quantity also has to be equal to E. Okay, so now you can see the point of what we were doing. Okay, so that the point of what we were doing is that our partial differential equation breaks into two equations. One of them involves x, and the other one involves time. Okay, so the time equation is that I h bar 1 over phi of t d phi dt is equal to E, and the x equation is minus h bar squared over 2m, 1 over psi of x, the second derivative of psi with respect to x, is also equal to, oh, whoops, I forgot the potential energy. Ha ha ha. Yikes. Plus v of x is equal to E. And here, these things have to be the same E. Okay, so it's like divide and conquer, right? So now we've separated out the x dependence and the time dependence. Okay, so what can we do with this? Okay, well, first, let's think about the time equation. The first of those things. Okay, so here we can multiply through by phi of t. Once again, now that these things are separated. So we get I h bar d phi dt is equal to E times phi of t, just that, E of phi t, right? Or better yet, if we divide through both sides by I h bar, this cancels. Okay, so we just have an equation that says the derivative of phi with respect to time is equal to some constant times phi itself. Okay, so that is a type of differential equation which you may have seen before, right? Have you ever seen any differential equation where the derivative of a function is equal to a constant times the function, right? Somebody tell me what the answer to that is.
Exponential.
An exponential, yes, that's right, okay? So the solution to that has to be that phi of t is some constant times e to the, this coefficient times time, right? And so e to the, wrong pen, capital E time over I h bar. Or this might be more commonly written as a constant times the exponential of minus I e time over h bar, because 1 over I is equal to negative I. Okay, well, this is pretty good. We solved the time part. So we get this expression in terms of the exponential, complex exponential in time. So this is now, wait, sorry, I'm confused by this. Okay, so this is now our time solution, okay? Now, for this constant piece, well, you remember we have the psi of x and t, the capital psi of x and t that we're looking with is phi of x times the function of time, right? Times psi of x times phi of t. So it's psi of x times this constant, the exponential of minus I energy t over h bar. Typically, what people do is they take this constant and they say, oh, well, I'm going to shove it into the psi, the thing that I haven't solved for already. And so we'll just say phi of t is equal to exponential minus I t over h bar. And put the constant into the thing that we haven't solved for yet. Okay. That takes care of the time-dependent part. Now, we still have the position-dependent equation. That is the big job. Okay, so let's go back to what is the position-dependent equation. Okay, so that is this thing. Let me copy that. Okay, so we have this equation to solve, all right, and we can now multiply again by both sides by the psi of x function. Okay? So we get minus h bar squared over 2m, this second derivative of psi with respect to x, plus v of x, psi of x, is equal to e times psi of x. Okay, so this is a special equation, which we will be coming back to all throughout the semester. Okay, so this is what we get if we take Schrodinger's equation and do the separation of variables, and then the time part was not so hard to solve, okay, but we're now left with the position part. Okay, so this is the Schrodinger equation with the time dependence taken out. The time dependence is already solved for. Okay, so the word that people use for that is the time independent Schrodinger equation. And the original Schrodinger equation that we were working on, I don't know, back here, for example, people might call this the time-dependent Schrodinger equation. So the time-dependent equation is really the fundamental equation that governs quantum mechanics. Okay? The time-independent equation is what happens if we have partially solved the problem. Okay, so we've partially solved it by solving for the time dependence, and this is what's left that we haven't solved for yet. Okay, and so this is, you know, what people mostly work on in quantum mechanics research. All right, so now there's a lot that we can say about interpreting this equation even before we put in some specific V of x potential energy function. Okay, so let's first think about the interpretation of what this means. Okay, so let's concentrate first on the first term over there. Okay, what I want to show you is that this term is related to the momentum operator that we were talking about in the last class. Okay, so you remember that the momentum operator that we want to stick into the integral sandwich to get the average momentum, okay, that is minus I h bar d by dx. So the momentum squared operator that we stick into the integral sandwich to get momentum squared, average, that is two of these things, minus I h bar d by dx minus I h bar d by dx, right? So that is negative h bar squared, whoops, not over anything. It's negative h bar squared times the second derivative, d2x, d2 by dx squared. Okay, so what about kinetic energy? I think I briefly mentioned that in the last class. That is p squared over 2m. Okay. So the operator for that we want to put into the integral sandwich, if we choose to get the average kinetic energy, that's minus h bar squared over 2m, second derivative with respect to x. Well, now, if we look in the time-independent Schrodinger equation, that is what is written right here. Okay, that this thing looks like the this looks like the kinetic energy operator acting on psi. Okay? That the thing that I circled here is just what you would put into the integral sandwich to get the average of the kinetic energy. Okay? Now, let's look at the second term here. V of x is the potential energy. So V of x, well, it is the potential energy. If we wanted to be fancy, we could say it's the potential energy operator because it's just multiplying psi. It operates on psi by multiplying psi. And the V of x is what you would stick into the integral sandwich to get the average potential energy. Okay. So now the thing that's on the left side of the time-independent Schrodinger equation looks like the sum of two things acting on psi, a kinetic energy acting on psi and a potential energy acting on psi. Okay, so our equation looks like the kinetic energy operator plus the potential energy operator, which are both acting on psi, and that combination equals E times psi. Okay, so here we have kinetic energy plus potential energy, right? Well, what you're familiar with from, say, university physics, right, is that the kinetic energy plus the potential energy equals the total energy. And then, if you've gone on in classical mechanics beyond university physics, right? You may have learned about some more advanced concepts with energy, right? And you know that the total energy, or the kinetic plus the potential, that's called the Hamiltonian, right? Um, is that word familiar to some of you guys? As a Hamiltonian operator, you may have seen in classical mechanics classes, right? People talk a lot about Lagrangians, right? The Lagrangian is the kinetic minus the potential energy. And so one way to set up classical mechanics is based on the Lagrangian operator, or just say the Lagrangian period. It's based on the Lagrangian, right? And another way to set up classical mechanics, which you might or might not have covered in a classical mechanics class, is based on the Hamiltonian, right? The kinetic plus the potential. And so in quantum mechanics, people use that concept all the time. Okay, so this total energy, so the kinetic energy operator plus the potential energy operator, this is called the Hamiltonian operator. Okay? And it is represented by the symbol H with a little hat over it. Okay, and this little hat is the symbol for operator. Okay, so in this sense, the time-independent Schrodinger equation then becomes that the Hamiltonian operator acting on psi is equal to E times psi. Psi of x, E times psi of x. So, okay, so this is a really, compact way of writing the time-independent Schrodinger equation. All right. So this then is going to be the equation that we want to work with, okay? And we want to solve it for specific potential energy functions, okay? Now, before I actually get into the first example, which I will do next week, I want to mention a couple things that Griffiths says that are kind of mathematical points, okay? And so I'll try to give you the highlights of Griffiths' more mathematical points. So from the textbook, okay, there is a section that is written as something like, what's so great about separable solutions? Separable solutions, okay. So the separable solutions, separable means solutions that satisfy this assumption of separation of variables. Okay. So I told you before, these are special solutions. Typical generic solutions are not like this, but these are some special solutions which are really great. So what's so great about them? Okay. Great thing number one. We know how they depend on time. Okay, so we know that psi of x and t is some function of x times what we already solved for, the exponential of minus I e t over h bar. Okay, and what about the complex conjugate? Well, that's going to be the complex conjugate of this function of x times the exponential of I e plus I e t over h bar. Whoops, now I'm scared somebody's going to raise his hand or her hand and ask, well, how do you know E is real? Capital E is real, because what I just did is assuming that capital E is real. Well, it is. I'll prove it later. It is real. I'll prove it coming up. Okay. So supposing that's true. Okay. Now, what about the probability density? Right? Well, we know the probability density as a function of x and time. That is psi star times psi. Okay, this is of x and t, of x and t. Okay, but now let's take these forms and plug them in. Okay, that gives us, oops, psi, a little psi star of x times little psi of x. And then these exponential factors just cancel. Okay, so the probability density, it depends on x, but not on time. Okay, so this is one really remarkable feature of these special solutions. Okay, so the word for that is that these things are stationary states. Stationary meaning not moving in time. Okay, so independent of time. Well, it's not that the wave function is independent of time. The wave function depends on time in just this way that we figured out, meaning that the real and imaginary parts are changing in time, but the magnitude doesn't change in time. And so we could say the probability density is independent of time. And likewise, the expectation values, all the expectation values of x and momentum and whatever, those things are all independent of time. Okay, so that is a remarkable thing to figure out, okay, with these separable solutions. Okay, now let me show you another cool thing about the separable solutions. Okay, suppose we want to know the expectation value of the total energy. So I showed you last time how to get the expectation value of the kinetic energy. Right? That is this integral of psi star of x and t, and then minus h bar squared over 2m, second derivative with respect to x, psi of x and t dx. Okay. The expectation value of the potential energy is likewise the same thing in the integral sandwich with the v of x. Okay. What about the expectation value of the total energy, kinetic plus potential? Okay. Well, that will be, I'll write it out in words first. Average of the total energy is the average, the sum of these two things. So minus h bar squared over 2m times this second derivative plus v of x, psi of x and t dx. Okay, well, that is actually the expectation value of the Hamiltonian operator. So everyone would always write this as the expectation value of the Hamiltonian operator, like that. Okay. Now, we can actually figure out what this is, okay? So this involves the Hamiltonian operator acting on the wave function, okay? If psi of x and t is one of these separable states, to the minus I e t over h bar, then the Hamiltonian operator acting on this thing is the same as the Hamiltonian operator acting on little psi times this exponential factor. And we know what the Hamiltonian operator does to little psi, right? It is equal to E times little psi, e to the minus I t h bar, t over h bar, okay? So in that case, all of this stuff is equal to an integral of psi star of x. We have this positive exponential times e times psi of x, and then this negative complex exponential, integral dx. And now we can simplify this business, right? Here, these exponential factors cancel out. And this is equal to, well, we factor out the e, it's a constant. We have this integral psi star psi dx, but this integral is equal to 1. That's the normalization. So this tells us now that the expectation value of the Hamiltonian in one of these special states is E, okay? So that then becomes the physical meaning of E. I didn't tell you before what E stands for. Now I can tell you. E stands for energy, okay? E is the energy. It is the expectation value of this Hamiltonian, the total energy operator. And energy is a physical thing, which is real. That's what I wanted to prove before. It is a real, not a complex number. Okay, so this is another important thing that we learn from working with these separable states, that the energy, the parameter E is the energy, which is the expectation value of the Hamiltonian operator. Okay, I have a couple other brief things I want to say in general, but I'm kind of out of time, so I will pause it here and continue on with this next Monday. And then after the general remarks, we'll get to a specific example, and then we can actually get a solution for some example. All right, I will stop here. I hope you all have a good weekend, and I'll see you on Monday. But of course, I'll stick around to answer questions about the science or the homework or anything else. Thanks.